So this is the second part of atomic theory, looking at electrons in atoms. And what we really want to focus in on this one is electron configuration. So understanding how to write out where the electrons live. The whole point behind this is so that soon we can understand how these different elements bond together either in ionic bonds or covalent bonds. We'll get to that a little later on, but first we need to get this background knowledge to understand electron configuration. So if we go down to the next slide, this is actually a summary from part one, and before I get to that, if you didn't watch part one, it was mostly informative, and I have to apologize for the beard. It's November in Montana, and every year we do No Shave November beard. Some places around the world it's called Movember, and so there's no shaving, and a good portion of my students, some of them ladies as well, have taken the oath to not shave in November, so later on down the line you'll see a clean shaven me up here at some point. This was something we filled out in part one, and just to reiterate, these are the different shapes or orbitals that are included when we're looking at atoms. And you'll have to go back to part one if you don't understand this, but for S there is one shape and it's spherical, and each one of them can hold 2 electrons. So one shape, 2 electrons, and this starts at the very first energy level, so the lowest energy level. We also have the P. There are 3 shapes in there. That means it can hold a total of 6 electrons. That starts at the second energy level. And then third, we've got 5 shapes for the D orbital. Each one of those can hold 2 electrons. That gives us a total of 10 electrons in there. And then the F has 7. Each one of those again can hold 2, and that starts at the 4th energy level. You may need to go back and check that out if that part doesn't make sense. So let's just sort of reiterate here. The first energy level only has the s orbital. It holds only 2 electrons, and it's written like this. So what you're going to start to see happen is we've got these codes, and it's how electrons are written out to explain where the electrons live inside an atom. So the second energy level has both s and p orbitals, 2 in the s and 6 in the p, as we just stated. So if we were going to combine these two things together, we would have, let's say, 1s2, 2s2, 2p6. And what this is telling us is we have 2 electrons. We have 2 electrons here in the s shape in the first energy level. We also have 2 electrons in the s shape in the second energy level, and we have 6 electrons in the p shape in the second energy level. So if we were going to count up these electrons, this example right here would have a total of 6, 2 more is 8, and 2 more is 10. This would be number 10 on the periodic table. If you went and took out your periodic table, which should have your trusty periodic table with you at all times for doing chemistry, you look over, you find number 10. Number 10 is neon. So this, now that it's all scribbled on, is the electron configuration for neon. So let's talk about filling order. There are 3 general rules that we need to follow when we're looking at filling order. One of them, and the way I teach it in my class, is we call these the 3 rules, and this would be number 1. They're not necessarily rules or laws, but more explanations of what happens. So this one is the Aufbau, okay, and it says that electrons enter the lowest energy orbital first. I'll explain that coming up. The second one here is the Pauli exclusion principle, at most 2 electrons per orbital, and they spin in different directions. That will make sense, I hope, here in just a couple of slides. And then the last one is Hund's rule. It states that when electrons occupy orbitals of equal energy, they do not pair up until they have to. Again, as long as you just know that those are the rules we're going to follow, you'll see those come out in a few slides. So, just to sort of reiterate, we're going to start filling up the lowest energy level first. The energy levels overlap, and we're going to use a counting system. So this is the first tool I'm going to give you. Really, you're going to end up with 3 tools, and the way I explain this in class is that we're trying to screw in a Phillips screw. and I'm going to give you 3 different screwdrivers, one of varying sizes. And this tool, at some point, they're all going to do the same thing, but one of them may be more useful to you at any given time. And for some people, one way really makes sense, another way does not make sense. So you're going to see 2 of those here, and it won't be really until the next unit where I'll show you probably the oversimplified version by just using the periodic table. But for now, to get the background knowledge and understanding of where this comes from, this will be the first one that I'll use. Now, from earlier on, from the beginning of the lecture in part 1, you saw that I had built a ladder. And let me get my pen back up there. Had built a ladder, and these were the rungs of that ladder. So we've got 1, 2, 3, 4, 5, 6, 7, where this was the nucleus. And these are different energy levels. So the further you get away from the nucleus, up here, the greater the energy. This is sort of analogous to that ladder, but because the atoms don't necessarily work in a perfect way that works with my model of the ladder, you have to more or less show it like this, where they're shifted. And what this is saying as these move is that, for example, the 2p here has a little bit more energy than the 2s. So it has to be a little bit higher up on this ladder of increasing energy. Now we're going to fill these in with arrows. So, as an example, that back there, let's determine the electron configuration for phosphorus. First of all, we need to find phosphorus on the periodic table. If you look over here, phosphorus is number 15. So, we've got 15 electrons we need to place. The number 15 means it has 15 protons, but we're going to assume that it also has 15 electrons and that they're evening each other out. So the first 2 electrons go into the 1s orbital. Now they have opposite spins. You need to remember which rule that comes from, so we show them this way in the orbital diagram to show that they have opposite spins. Alright? And we have 13 more that we need to place. Notice the first 2 fit into the 1s, so technically that would be the 1s to the 2nd power because it has 2 there. We'll clear that up in just a moment. The next 2 electrons go in the 2s, and now it's full, but we still have electrons left over. We have 11 of them, so we need to put more of them. We move our way up the ladder. This is sort of just like filling up this ladder with water. Whatever you encounter next is where you need to put the next electrons. So we can fit 6 in the 2p. We still have some left over. When we get to this point, we have 3 more. So those will go in the 3p. We're working our way up the ladder. But notice what starts to happen here, and this is important. According to Hund's rule, they do not pair up until all energy levels are full. So this is the correct electron configuration in the orbital diagram here for phosphorus, which has 15 electrons. Now, let's say we were going to move up to something that had more electrons. If we went up to 16 electrons, which would be sulfur, or 17 with chlorine, either way, if we had 16, we'd need to put another one here. If we had 17, we'd put one here. If we had 18, we'd put one here. If we had 19, we'd add one up here, 20, and so on and so forth. And then we would need to jump over here. But we'll get into those higher levels a little later on. And this is how we would write this out. So we've got 2 electrons in the 1s as shown in the orbital diagram. Right here, 2 electrons in that. We've got 2 in the 2s. We've got 6 up here in the 2p. We've got 2 in the 3s, and we've got 3 up here in the 3p. This is the electron configuration for phosphorus. Now, some people think that that's the easy way to remember it. But if you're going to use the orbital diagram like that, you need to probably write it out and draw in the arrows all the time. Personally, I think this is the easier way to do it, and this is the one I'll model over and over. But if that other tool works better for you, then continue to use that one. I'll explain why I think this one's a little bit easier in just a second, but what you're going to see is this is a little bit different way of doing it. We're going to use arrows to cancel these out. When the 1s is full, we write an arrow through it and we write out 1s2 because we know that the S shape holds 2 electrons, and if that one's full, then it has 2 electrons in it. If I need to have more electrons, so I'm working my way up the periodic table, and now I've got 4 electrons. If I need to fill those in, notice I work my way up and I fill out the 2s as well. So now I have 1s2, 2s2. If I need to add more electrons, in this case up to 12 electrons, I would fill up the 2p, then I would fill up the 3s, and you can see the p shape now holds 6. So when it's filled up, it's got 6 electrons in it, but all those s's up there have 2. Now next we're going to get into the 3p and then the 4s, so we'll cancel those out and they fill up. And then look, we need to jump over to the 3d, 4p, 5s. Now this is where people get confused. It goes back to that diagram before of varying energy levels. So the 4s actually has a lower energy level than the 3d, so it's going to fill up first. Now notice what happens if we have a whole bunch more electrons we need to put in here. We're going to fill up the 3d, and remember d holds 10. So if you're following this, you see 3d10, 4p6, 5s2, and we're up to 38 electrons. So we're working our way up the periodic table at 38 electrons. We're at strontium. And if we just keep on going, eventually we're going to fill this up till we get to 118, which puts us at the end of the periodic table at this point anyway, which is an octium. So if we were going to do this for titanium, first thing we need to do is find it on the periodic table. If I look over here, I find titanium right here, which is number 22. We know that that means it has 22 protons, so we're going to assume that it also has 22 electrons. And here's how we fill this out. So bear with me, I have to write on the iPad over here, and it kind of looks like I'm looking off to the side. So we need to get up to 22 electrons. Here's the easiest way to keep track in my mind. The 1s2, when we draw an arrow through it, we know that we've just used 2 electrons. So now we got 2 electrons. We still have 20 we need to take care of. The next line is going to go through here. The S shape holds 2. So if I was to total those 2 up, now I'm up to 4 electrons. I apologize, it's getting squished in there. Then I move down here to the 2p. The 2p holds 6. The 3s holds 2. That means that's a total of 8. If I add this 8 that I just put there with the 4 I had before, now I'm up to a total of 12. Again, I apologize for the writing there, but I need to get up to 22. So next I move down here to the 3p. I know that the 3p can hold 6, and the s can hold 2. So I've just added another 8 to this. I was at 12. I add 8 to that. Now I'm at 20. I need to get to 22, so I need to account for 2 more. Those next 2 are going to go right here in the 3d, but I'm only going to have 2 of them in there. Now here's how I write this out. I go back to the first ones I canceled and write them out just like we did before. For titanium, I write out 1s2. That's this right here. Then I go up here to the next line, and that was the 2s2. Then I go up here to the next line. I run through the 2p6, and then it runs through the 3s2. Then it runs into the 3p6, and I'm going to show that I'm starting over down here at the bottom. After the 3p6, I go to the 4s2, and finally down here to the 3d2. So that's my full electron configuration for titanium. You'll see it written a number of different ways, and it seems like general consensus now is to keep the numbers together. So 2p6, and then all these 3's would remain together. So we'd have 3, and actually, let me take a step back with that. So I'm really used to writing it out the full way. So this means that this 2 goes with the S and the P. Then you'd have a 3, which goes with the S2, P6, and D2. Then I ran out of room again, but then you would have the 4 S2. Both of these are correct, and it seems like this tends to be general consensus, but I still prefer doing it this way, especially when you're learning how to write these, to keep everything in order from lowest energy level, working our way up. So that takes us through electron configuration. In the next section, part 3 of this, we're going to look at electron configuration with noble gases. So if you're looking to figure out how to write the noble gas configuration for this, find part